welcome to this problem walkthrough. Today, we'll be exploring problem number 1625, titled Lexicographically Smallest String After Applying Operations. Together, we'll dive into the solution approaches, analyze their complexities, and understand how to effectively tackle this challenge. Let's get started. In this problem, we are given a string S, which has an even length and consists of digits from 0 to 9. Along with the string, we are provided two integers, a and b. The task involves applying two types of operations on the string as many times as desired and in any order. The first operation is called the add operation, where we add the integer a to all odd indexed digits of the string. It's important to note that the digits wrap around to 0 once they exceed 9, meaning the addition is cyclic. For example, if the string is 1234 and a is 5, adding 5 to the odd indexed digits results in 1739. The second operation is the rotate operation, where we rotate the string to the right by b positions. For instance, rotating the string 1234 to the right by 2 results in 3412. The goal is to determine the lexicographically smallest string that can be obtained by applying these operations. A string is considered lexicographically smaller than another if, at the first differing position, it has a character that appears earlier in dictionary order. Now, let's specify the input and output formats for the problem. The input includes the string S, which has a length n that is always an even integer between 1 and 100. The integer a lies between 0 and 9, and it is the value added to the odd indexed digits during the add operation. The integer b is between 1 and n, and it represents the number of positions for the right rotation. For the output, we need to return a string that represents the lexicographically smallest version of S that can be achieved using any sequence of the given operations. To illustrate how this works, let's dive into the examples. In the first example, the input string is S equals 5525, with A equals 9 and B equals 2. The process begins with a rotate operation, where the string is rotated to the right by 2 positions, resulting in 2555. Next, we apply the add operation by adding A equals 9 to all odd indexed digits. This transforms the string into 2050. After exploring all possible operations, the smallest lexicographical string we can obtain is 2050. Moving on to the second example, the input is S equals 74, with A equals 5 and B equals 1. First, rotating the string to the right by 1 gives 47. Then, adding A equals 5 to the odd indexed digits results in the string 24. This is the smallest lexicographical string obtainable for this case. For the third example, the input string is S equals 0011, with A equals 4 and B equals 2. Here, rotating the string by 2 positions does not change its arrangement because the string is symmetric, so it remains 0011. When we attempt to add A equals 4 to the odd indexed digits, the resulting strings are not lexicographically smaller than the original. Therefore, the smallest string obtainable remains as 0011. These examples highlight how the operations interact and how we evaluate the lexicographical order to determine the result. Now, let's consider the constraints and edge cases. There are several edge cases to keep in mind while solving this problem. First, for the minimal input size, when n equals 2, the operation should still work correctly, ensuring that both rotation and addition produce valid results. Second, if all digits in the string are identical, such as 1111 or 0000, neither rotation nor addition will affect the lexicographical order, so the original string will be returned. Third, when the rotation value b is equal to or larger than the length of the string, the rotation should wrap around properly, maintaining the cyclic behavior. Finally, if no sequence of operations can produce a lexicographically smaller string, we simply return the original string. These edge cases help ensure the solution is robust and handles all scenarios effectively. To tackle this problem, the brute force approach is the most straightforward method to consider. The idea is to generate all possible strings by exhaustively simulating the two operations provided. Operation 1 involves incrementing all digits at odd indices by a fixed value a, wrapping around at 10 using modulo arithmetic. Operation 2 rotates the string by b positions. By repeatedly applying these two operations in every possible sequence, we can evaluate all potential outcomes and track the lexicographically smallest string. However, there are some critical observations to keep in mind. Since the string has a fixed length and the operations involve modular arithmetic, the number of potential states is finite. Despite this, exploring all possible combinations can lead to exponential time complexity in the worst case, as many states may be revisited unnecessarily. While this approach guarantees correctness, it is computationally expensive and impractical for larger inputs, making it less suitable for efficient problem solving. To improve efficiency, we can employ an optimized approach using breadth-first search, or BFS. Here, we treat the problem as a state space search, where each possible string configuration is a state, and the two operations act as transitions between these states. Starting from the initial string S, we systematically explore all reachable states by applying both operations. Specifically, we add a to the digits at odd indices to generate one set of new states, and rotate the string by b positions to generate another. For each newly generated state, if it hasn't been visited before, it is added to a queue for further exploration. During this process, we track the lexicographically smallest string encountered. BFS is particularly effective here because it avoids redundant computations by marking visited states, ensuring that each state is only processed once. While the smallest number of operations isn't our primary goal, BFS naturally lends itself to systematic exploration, making it a practical and efficient choice for this problem. Although BFS significantly reduces computational redundancy compared to brute force, it still has its limitations. Memory usage can become substantial for larger strings, as we need to track all visited states. To address this, an alternative optimized approach leverages the mathematical properties of the operations. By analyzing the periodicity and constraints of the problem, we can narrow down the state space even further. Rotating the string by b creates a limited set of unique rotations, as the string's length is fixed. Similarly, adding a to the digits at odd indices produces a periodic pattern due to modulo arithmetic. Using these insights, we can systematically generate all distinct rotations of the string and, for each rotation, simulate the digit modifications until they cycle back to their initial configuration. This allows us to focus only on reachable and unique states, directly identifying the lexicographically smallest string without redundantly exploring the entire state space. By combining these mathematical insights, we can achieve a more efficient solution. The mathematical approach, while efficient, requires careful implementation to ensure correctness. Rotations and digit adjustments must be handled systematically to avoid missing any potential states. The time complexity of this method remains n squared, as we still need to evaluate all rotations and their associated digit modifications. However, the space complexity can be reduced to n, as we only track the minimal result and avoid maintaining a comprehensive visited set like in BFS. This makes the mathematical approach particularly efficient for larger inputs. Nonetheless, it introduces additional complexity due to the need for deeper reasoning about periodicity and modular arithmetic. As a result, while this approach minimizes computational overhead, its implementation may be less intuitive and harder to debug compared to BFS, especially for those less familiar with these concepts. The trade-off here is between computational efficiency and implementation simplicity. After evaluating the different strategies, the breadth-first search approach emerges as the most balanced choice for this problem. While the brute force method is conceptually straightforward, its computational expense makes it impractical for large inputs. The mathematical approach, on the other hand, is highly efficient but requires intricate reasoning about periodicity and modular arithmetic, which adds complexity to the implementation. BFS, however, strikes a balance between these extremes. It provides a clear, systematic framework for exploring state transitions, ensuring correctness through exhaustive exploration while avoiding redundancy by marking visited states. This makes the method both efficient and intuitive to implement, offering a reasonable trade-off between computational performance and conceptual simplicity. With a final time complexity of n squared and space complexity of n squared, BFS is well suited for problems of this nature, making it our chosen strategy for solving the problem. To solve this problem, we are tasked with transforming a given numeric string into its lexicographically smallest version by repeatedly applying two operations. The first operation allows us to add a given integer to each digit at odd indices of the string. If the resulting value exceeds 9, we take it modulo 10 to ensure it remains a single digit. The second operation lets us rotate the entire string to the right by b positions. These operations can be performed in any order and any number of times. To determine the smallest possible string, we must simulate these operations, explore all valid transformations, and identify the optimal result. A systematic approach is required, and the first step is to fully understand how these operations work and how they can be simulated efficiently. To efficiently search for the smallest string, we use a breadth-first search, or BFS, strategy. First, we initialize a queue with the original string S, which represents the starting point. At the same time, we create a visited set to keep track of all strings we have already processed. This prevents redundant computation and ensures the BFS terminates efficiently. As we process each string from the queue, we apply both operations, adding it to the digits at odd indices and rotating the string by B positions. Each resulting string is enqueued only if it has not already been visited. During this process, we continuously update the smallest string encountered so far. Special cases, such as when B is 0 and no rotation is possible, or when A is 0 and odd index digits remain unchanged, are handled separately to streamline the search. This approach ensures that our exploration is both exhaustive and efficient. The goal is to systematically explore all valid transformations while minimizing redundant calculations. Lexicographical order is the key metric for determining the smallest string, and this requires careful consideration of all possible states resulting from the operations. The addition operation relies on modulo arithmetic to ensure digits remain valid, while string slicing is used for efficient rotation without unnecessary character shifting. BFS is chosen over brute force because it avoids revisiting states, making it significantly more efficient. The two primary data structures involved are the queue, which supports the BFS traversal, and the visited set, which ensures we avoid infinite loops and redundant processing. Together, these structures allow us to simulate transformations systematically. The complexity of this approach is bounded by the number of unique strings that can be generated, which, while theoretically large, is often much smaller in practice due to overlapping states. The pseudocode demonstrates the detailed implementation of the BFS approach. We begin by initializing the queue with the original string S and marking it as visited. A variable smallest is used to track the lexicographically smallest string encountered during the search. In the BFS loop, we process each string by applying the two operations. For the first operation, we modify the digits at odd indices by adding and taking the result modulo 10. If the resulting string has not been visited, it is added to the queue for further exploration. For the second operation, we create a new string by rotating the current string by B positions. Again, if this string is unvisited, it is added to the queue. After processing all transformations, we return the smallest string recorded. This pseudocode ensures every valid transformation is explored with optimal efficiency. Let's walk through an example to clarify the algorithm. Suppose we start with the string 5525, with A equal to 9 and B equal to 2. Initially, the string is 5525. Applying the first operation, we add 9 to the odd indices, resulting in 5925. Next, applying the second operation, we rotate the string by 2 positions to the right, resulting in 2555. Using BFS, we repeat this process, exploring all possible transformations. As we continue, we track the smallest string encountered. Eventually, after fully exploring the transformation space, we find that the smallest lexicographical string is 2055. This example demonstrates how the algorithm systematically applies the operations and ensures that no valid transformation is missed. Here, we begin implementing the solution to find the lexicographically smallest string after applying the given operations. First, we import the deque class from Python's collections module to help with our breadth-first search approach. Inside the solution class, we define the findLexSmallestString method, which takes 3 parameters: the input string s, the integer a for the addition operation, and the integer b for the rotation operation. We initialize a few key variables: n to store the length of the string, visited as a set to keep track of strings we've already processed, q as a deque initialized with the input string, and smallest to keep track of the lexicographically smallest string found so far, initially set to s. The main logic is implemented within a while loop that runs as long as there are elements in the queue. At each step, we dequeue the front element, and if it's already been processed, we skip it. Otherwise, we add it to the visited set. Next, we check if the current string is smaller than our smallest string, and if so, we update the smallest variable. Then, we implement the first operation, where we add the integer a to each digit at the odd indices of the string. Using a loop, we modify the appropriate indices, keeping the new digits within the range 0 to 9 using modulo 10 arithmetic. Finally, we join the modified list back into a string and append it to the queue if it hasn't been visited already. The next step in our implementation is to handle the second operation, which involves rotating the string by b positions to the right. This is achieved by slicing the string. We take the last b characters and move them to the front, followed by the remaining characters. The resulting string, new_rotate_up, represents the rotated version of the current string. If this new string has not been visited yet, we append it to the queue for further exploration. Once the while loop completes, meaning all possible transformations have been processed, the function returns the smallest string that was found during this process. This breadth-first search approach ensures that all valid transformations are considered, and by maintaining the smallest variable, we efficiently identify the lexicographically smallest string. With this, the implementation is complete, and we've ensured both operations are applied systematically to explore all possibilities. Here, we start by importing the necessary utilities, such as set and queue, which will be used in our implementation. The method findLexSmallestString accepts three parameters: the input string s, an integer a, and another integer b. First, we determine the length of the string and initialize a visited hash set to keep track of strings we've already processed. We also use a queue to manage the breadth-first search, adding the initial string s to it. The variable smallest is initialized to store the lexicographically smallest string we encountered during the process. In the while loop, we process each string in the queue. If the current string has already been visited, we skip it, otherwise, we mark it as visited. Next, we check if the current string is smaller than the smallest string we found so far, and if so, we update smallest. Then, we proceed with the first operation, where we add the value a to each digit at the odd indices of the string. To do this, we convert the string to a character array and iterate over the odd indices, updating each digit accordingly. After modifying the digits at the odd indices, we construct a new string called newAddUp using the updated character array. If this new string hasn't been visited yet, we add it to the queue for further processing. Next, we implement the second operation, which involves rotating the string by b positions to the right. To achieve this, we use substring operations to split the string and rearrange its parts in the required order. The result is stored in the variable newRotateUp. Again, if this rotated string hasn't been visited, we add it to the queue. The while loop continues processing strings in this way, applying the two operations and checking each resulting string until the queue is empty. Finally, when all possibilities have been explored, the method returns the smallest string found, which is stored in the smallest variable. To solve this problem, we use a breadth-first search (BFS) approach. Starting with the initial string s equals 5525, we initialize key components to track the process. The visited set ensures we don't revisit states, the queue helps us explore all possible transformations level by level, and smallest keeps track of the lexicographically smallest string encountered so far, which is initially set to 5525. In the first level of BFS, we dequeue the string 5525 and mark it as visited. Now, we apply the two possible operations. For operation 1, we add a equals 9 to the digits at odd indices. Specifically, adding 9 to the digits at index 1 and index 3 results in the string 5424. We add this new string to the queue for further exploration. Next, we consider operation 2, which involves rotating the string 5525 by b equals 2 positions to the right. This produces the string 2555, which we add to the queue. Now, moving to the second level of BFS, we dequeue 5424 and mark it as visited. We also compare it with the current smallest string, updating smallest to 5424, as it is smaller than 5525. We then apply operation 1 on 5424, adding 9 to the digits at indices 1 and 3, resulting in 5323. This string is added to the queue. For operation 2, rotating 5424 by 2 positions produces 2454, which is also added to the queue. At this point, the queue contains 2555, 5323, and 2454. The BFS process continues by dequeuing each string, applying operations, and tracking the smallest string encountered. This ensures we explore all possible transformations systematically. Eventually, after all states are explored, the lexicographically smallest string for this example is found to be 2050. Now, let's move on to a second example where the input string is 74, with A equals 5 and B equals 1. Similar to the first example, we initialize the visited set, the queue with the initial string, and the smallest string set to 74. We then proceed with the BFS process, starting by dequeuing 74 and marking it as visited. Here, applying operation 1 to 74 means adding A equals 5 to the digit at the odd index, which is index 1. This transforms 74 into 79, and we add 79 to the queue. Next, applying operation 2 rotates the string 74 by B equals 1 position, resulting in 47. This is also added to the queue. In the second level of BFS, we dequeue 79, mark it as visited, and compare it with the current smallest string. Since 74 is still smaller, smallest remains unchanged. When we apply operation 1 to 79, it transforms back to 74. However, since 74 is already visited, we skip it. For operation 2, rotating 79 produces 97, which is added to the queue. We then continue the BFS process, exploring the remaining strings in the queue. By the end of this exploration, the lexicographically smallest string for this example is determined to be 47. In conclusion, the smallest strings for the two examples are 2050 and 47, respectively. This demonstrates how BFS, along with careful tracking of visited states, enables us to systematically explore all transformations and find the optimal result. To analyze the time complexity of solving this problem, we need to break it into two main components: the operations themselves and the breadth-first search traversal of all possible states. Let's start with the number of possible states. When applying the addition operation, digits at odd indices are altered independently. Since there are 10 possible values for each digit, this gives us a total of 10 raised to the power of n/2 unique strings, where n is the length of the string. Then, the rotation operation can produce up to n distinct shifts of the string. Combining these, the total number of unique states is bounded by 10 n/2 multiplied by n. Now, for processing each state, the addition operation involves iterating over half the digits, which takes n time. Similarly, the rotation operation also takes n to execute. Checking and adding states to the visited set or queue is constant time, 1, due to the use of a hash set. Therefore, processing each state has an overall time complexity of n. Now, let's focus on the BFS traversal. In the worst case, BFS needs to explore all possible states. Since we just established that the number of states is bounded by 10 n/2 multiplied by n, and each state takes n to process, the total time complexity for BFS can be expressed as number of states * processing time per state. This simplifies to 10 n/2 *n*, which is n squared * 10 n/2. For space complexity, let's start with the visited set. This set stores all unique states encountered during the traversal, and as we determined earlier, the number of unique states is bounded by 10 n/2 *n. Since each state is represented as a string of length n, the memory usage for the visited set is n * 10 n/2 *n, which simplifies to n squared * 10 n/2. The BFS queue has a similar space requirement, as it can grow to hold all unique states in the worst case. Each string in the queue contributes n space, leading to a total memory usage of n squared * 10 n/2 for the queue as well. Additionally, we need to consider auxiliary space. Temporary variables like the array used for the addition operation and the strings generated during rotation require n space. However, this is negligible compared to the space required by the visited set and the queue. Thus, the overall space complexity is dominated by the visited set and the queue, both of which have a complexity of n squared * 10 n/2. Now, let's compare this optimized BFS approach to a brute force solution. A naive approach would involve generating all possible strings by applying every combination of addition and rotation operations, then sorting them to find the lexicographically smallest one. This would result in an exponential number of combinations, with a time complexity of 10 to the power of n*n, which is vastly worse than the BFS approach. On the other hand, the optimized BFS solution takes advantage of the visited set to prune redundant computations, ensuring that only reachable states are explored. This significantly reduces the time complexity and makes the approach far more efficient than brute force. Finally, let's discuss the best and worst case scenarios. In the best case, if the input string is already the lexicographically smallest and no operations are needed, BFS terminates almost immediately. The time complexity in this case is 1. In the worst case, however, BFS must explore all possible states, which results in a time complexity of n²*10 n/2. The same applies to space complexity in both scenarios. To justify the big O analysis mathematically, we rely on the bounds for the number of states, which is 10 n/2 *n. The addition operation gives 10 n/2 possibilities, as it independently alters digits at odd indices, while the rotation operation has n possibilities based on the number of shifts. Processing each of these states costs n, which leads to the overall complexity of n²*10 n/2. This analysis explains why the BFS solution is both time efficient and space efficient compared to brute force. One common mistake to watch out for is applying operations in the wrong order. When multiple operations are allowed, their sequence matters. Some operations don't commute, meaning the result of one depends on the state left by the previous. This can lead to incorrect outputs if the order is not carefully followed. Another frequent oversight is ignoring constraints or edge cases. For example, failing to handle empty strings, single-character strings, or boundary values like the maximum input size can cause runtime errors or incorrect results. Additionally, modulo arithmetic is often mishandled. When adding a value like a modulo 10, it's crucial to ensure the result wraps around correctly. For instance, 9 plus 2 modulo 10 should give 1, not 11. Finally, avoid using inefficient brute force approaches on large inputs. Generating all possible combinations without optimization can lead to exponential growth in complexity and result in time limit exceeded errors during execution. Another mistake to be cautious of is overlooking the nuances of lexicographical order. For example, when comparing strings, remember that 123 comes before 213 because 1 is smaller than 2. Misunderstanding or misimplementing these rules can produce incorrect answers. Now, when solving this problem in an interview, focus on identifying patterns or invariants in the operations. For instance, adding it to digits at odd indices repeatedly may create a cycle due to modular arithmetic. Instead of brute forcing all possibilities, you can optimize by exploring these cycles or pruning unnecessary computations. Be sure to communicate clearly with your interviewer, discuss edge cases, clarify constraints such as whether duplicate results are allowed, and analyze trade-offs in your approach. Additionally, be prepared to evaluate the time and space complexity of your solution. For instance, a brute force approach might have a time complexity of n*k, where n is the string length and k is the number of transformations, while storing all transformations could require significant memory. If you're looking to deepen your understanding of similar problems, here are some related ones. LeetCode Problem 31, Next Permutation, focuses on generating the next lexicographical order, which requires understanding how to manipulate sequences efficiently. Problem 60, Permutation Sequence, is another example that deals with permutations but emphasizes efficiency. Problem 89, Gray Code, involves generating sequences under specific rules, similar to how transformations operate in this problem. Lastly, Problem 296, Best Meeting Point, highlights optimization in sequences but with a focus on minimizing cost, another skill relevant for reducing computational overhead here. Now, when considering alternative solutions, brute force is a straightforward approach. It's easy to implement and works well for small inputs, but it's inefficient for larger ones and might time out due to its computational complexity. For more efficient approaches, a greedy algorithm can be considered. This method attempts to make locally optimal choices at each step, minimizing computations. However, while it's computationally efficient,
it doesn't always guarantee the globally optimal solution. Another option is breadth-first search, or BFS. BFS systematically explores all possible transformations level by level and guarantees the shortest path in terms of transformations. The downside is that it requires more memory to store the queue. Finally, you could leverage mathematical cycles or modular arithmetic. This approach exploits periodicity in the operations to reduce the problem space significantly. It's highly efficient, but it demands a deeper understanding of the problem structure and how modular arithmetic interacts with the transformations. Each of these strategies comes with trade-offs, so it's important to choose the one that best fits the problem constraints and input size. Great job sticking with me through this walkthrough. To summarize, we tackled the problem by exploring a brute force approach and discussed the importance of lexicographical order and trade-offs in algorithm design. Thanks for your time, and I hope this was helpful. Don't forget to like, subscribe, and stay tuned for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!